Okay, so welcome everyone. Welcome back after the after the summer break. So we are restarting now our series of seminar, and today we have the pleasure to have Giulia Migliori with us. So Giulia is currently a staff researcher in Bologna at the Institute for Radio Astronomy since 2020. But before landing back to Italy, where she defended her PhD at CIS and Trieste in 2010, she was a bit around for a couple of postdocs, first in CFA in Boston, and second in in Paris. So Giulia's interest and research spans different topics, I would say, from compact object, stellar, and supermassive black hole to evolution of radio galaxies, young radio sources that she mostly studied using high energy emission observation and modeling the broadband emission in these sources. Today she will give us a talk on the high energy view of extragalactic young radio sources. And one last thing, Giulia is with us until tomorrow, and she's in Dima's office, so whoever wants to pass by and talk with her, we find her there. So thanks.
So I start thanking a lot for the invitation. So I will be the opening talk. It's the first time I'm the opening of a season. So thank you again. It's very nice to visit here. Today, as Carolina was saying, I will try to give an overview, incomplete probably, overview on young radio sources seen from a high energy perspective. And before starting, I would like to acknowledge my collaborators, and in particular, these three persons in the first line. Aneta was the first enthusiast on high energy studies of young radio sources. Then in the last years, Małgosia Sobolewska, that maybe you have seen also in the conference, has done a lot of work on X-rays, in particular studies, and Monica Orienti, who is my reference for whatever is the radio observation, and we are still collaborating. We have a lot of works ongoing still right now. So let's start. As usual, there is no. Okay. Let's start. This is the outline of the talk. I will briefly define what we mean for young radio sources and give some motivation in terms of evolution and feedback to study them in the high energy. Then I give a bit of introduction on what are the expectations, the prediction from the point of view of theory for the high energy emission of these sources, and then I move to observation. I will touch upon some multi-wavelength modeling before coming to the conclusions. So young radio sources. I would like to define to start with as maybe the only extragalactic radio AGN that are down to the human time scales. And this is because based on their compact sizes and expansion velocities, their estimated ages can be as low as 10 to 1,000 years. So this is the case of, this is the radio image of one of these young radio, compact radio source, where you see the estimated kinematic age based on the linear size and the advanced velocity of the edges are hundreds of years. And I was just hearing in these days that this Italian lady just won the worldwide competition for 200-meter race. And if you want, you can, and she's 90 years old, so just some factors younger than the source. And if you want, you can make the mass of her velocity in terms of subluminal motion. But going to more serious definition, what we do typically is to classify them from the morphology, from the morphological point of view, and usually the classification relies on their symmetric radio structure, making a sequence from compact symmetric objects that are typically smaller than 1 kiloparsec to medium symmetric one that are within 20 kiloparsec, and then large symmetric one. The traditional classification was instead relying on the radio spectrum and on the fact that they display typically a peaked spectrum, and the spectral classification is referring to the position of the peak in the radio spectrum, going from the high frequency peak sources that are typically the most compact to the gigahertz peak, to the compact size, or megahertz peak spectrum that are compact steep spectrum that are peaking in the megahertz regime that are the more evolved sources. So let's say that there is a relation between the linear size and the position of the peak frequency in the radio spectrum, and of course, as I said, a relation also between the linear size and the estimated age of the radio structure. Yeah, sure.
So in the plot that you're showing,
yeah,
it's a bit mix and match in the different groups between morphological and spectra.
Yes.
You see a few words on what the morphological classes are and what the spectral classes are, just so that we can understand.
Yeah, no, I was going to describe the plot. So in this plot, in fact, it's the size and the radio power. And as you see, as it was noticed, it's a bit mixed because now we are basically moving more to the morphological definition. That is the one that we consider maybe more reliable and less prone to be contaminated from other kind of sources that display also peaked spectra, like blazar sources. So here, I mean, the CSO are the most compact, and they overlap largely with GPS, which is a sample of typically identified from the radio spectrum, but they also display, for example, compact symmetry. The problem is that GPS may, as a class, may include radio galaxies and also quasars. CSO typically exclude quasars. And the same also for CSS. Also in this case, the spectral classification may include both radio galaxies and quasars, while instead, let's say, the morphological classification is typically selecting more radio galaxies, so more misaligned sources, where we can be sure that projection effects are not artificially giving the impression of a smaller size. So let's say that ideally, having more sources, here we should have CSOs, MSOs, LSO, and then moving to the higher evolved sources, to FR1, FR2, that are the classical radio galaxies. Then the studies and the classification evolved in the year, and so this is why in this source we have including a bit both both samples with different kind of classifications. So let's say that I will try to stick more to CSOs that are the truly compact, the most reliably compact, but at some point you will see that I will have to move also because of lack of target also to the GPS and CSS. But typically for now, we stay on the morphological classification. So as I was mentioning, there has been a lot of work, especially from the radio people, to obtain reliable classification of intrinsically compact sources. And in particular, recently, a lot of enormous work was undertaken by this group here that went through all the samples and reached obtained finally a sample of bona fide CSOs, which were selected through morphological, but also mainly morphological criterion, but also including variabilities and all a set of criteria that gave this final sample. And proposed also, here you can see a compilation of the sources, and proposed also a sub-classification of CSOs, distinguishing between edge dim and edge brighten, a bit recalling the classification that we have also for the most evolved sources. Also, another conclusion that they were reaching is that when we talk about CSO, it's not forgiven that all of these sources are in fact only young, because when we compare the number of CSOs in flux limited radio samples with evolved sources, it seems that there is an overabundance of some of the CSOs, meaning that not all probably are reaching the evolved stage, and some could instead simply be a short-lived phenomenon of the radio activity. And something similar is also shown in this schematic, in this sketch, where we have young radio galaxies, then the adult phase, but a fraction that is actually a significant fraction, probably is like having an intermittent activity, if not directly moving to the remnant phase, where basically the larger the jets and the lobes are just fading away. So this also motivates, in fact, the studies on the high energy studies, because one of the points is to understand what are the initial conditions of the radio sources, and what determines the fact that some are moving to the expand to the kiloparsec and megaparsec scales, and other instead switch off earlier. The other point is that according to numerical simulation, this is a phase where we expect a strong coupling between the expanding radio source and the interstellar medium of the host galaxies where the source is located in. This is just an example of one of these simulations where the source is going toward a fourth phase where the expansion could be confined and possibly even frustrated, or instead continuing emission breaking out of the host galaxies and reaching the classical phase. Again, in this phase, it's important to understand what are the parameters of the environment and of the source that discriminate between the evolution, between the different evolution, and also how in this phase the radio galaxy is releasing energy into the ambient medium, because this, of course, can on the other side impact the evolution of, for example, stellar formation, quenching or enhancing the star formation of the host galaxy. So to obtain a complete view, the high energy point is clearly being one of the highest, most energetic radiation, is clearly a key point to study. Do we expect high energy emission from this source? Of course, yes, because once that you have an AGN, as also normal and the radio quiet AGN, we do expect X-ray emission produced from the central AGN. But on top of that, the fact that we are talking about a compact radio structure may also imply that high energy emission is produced both in the jets, and in this case, what we have are different kind of contribution. Broadly speaking, I would say that we have similarly to jet in blazars, for example, we expect that the emission is dominated by inverse Compton on different seed photons, and the seed photons can come both from the jet himself, being the synchrotron photons produced by the jet, but given the tiny dimension of the source, can be also the one in the nuclear region, so the disk ultraviolet photons, the photons from the dusty torus, and for example, even the photons from the broad lines, because I just remind that we are talking about linear size that are tens of parsec. So in this case, for example, I was doing some study on the jet contribution, considering different initial jet power and luminosities of the accretion disk, of the torus, and so on. And I was trying to estimate it with the increasing linear size of the source, the contribution from the jet in the X-rays and in the gamma ray band, and how this change according to different jet parameters. But yeah.
Wouldn't that emission though be beamed?
Of course, yes.
We see these are symmetric sources, they shouldn't be.
Yes, so in fact, this from the jet would be non-thermal beamed emission. And then it depends also on how fast the jet component is moving. So for some of these sources, and maybe I have the time to discuss more later, some of the bulk motion are relatively low. So yes, so meaning that the beaming can be strong or not so strong, depending on yes, what are the assumptions on the jet speed. And so, for example, even for misaligned, relatively misaligned sources, we could have still considerable flux. And the other are, of course, the lobes. I'm saying something more in the following slide. I won't touch too much on this, but keep in mind that the interaction between the expanding structure and the ISM can also produce X-ray thermal emission. So the lobe, this is particularly interesting for compact symmetric object because, as we said, we expect in this case the expectation is that the emission is isotropic because the lobes are not moving highly relativistic, is a subrelativistic expansion. So in this case, given their compactness, what was demonstrated in particular in this work is that in the first for the most compact and most compact sources and sources with also luminous disk, we can have a high fraction of X-ray and gamma rays luminosities produced by Compton scattering of the UV luminosity from the disk by the electrons contained in the overpressured lobes. Similarly, so this would mainly dominate the gamma rays, while instead Compton scattering of infrared photons from the dusty torus would still produce a high level of X-ray emission. The interesting point is that the level of this emission is supposed to change with the expansion of the source. And of course, the other point is, as I said, that it's expected to be an isotropic non-thermal emission. So in particular, this model was not only a radiative model, but also a dynamical model. So it was basically following up the expansion of the source and then producing the expected flux from radio to multiband flux from the lobes. So then let's move to from the theory to the observation. And before starting, I would like to point out some challenges that we are facing when we do high energy observations. So as you see here is another image, a beautiful image with the VLBA of a compact symmetric object where we clearly resolve the radio structure. Here we are on milliarc second scales. Okay, this is the same source observed by Chandra. Here all the emission, not only of the source, but also of the galaxies is contained in 1.5 arc second. That is the PSF of the instrument. When we go, and this is in the soft X-ray regime, when we go to even harder X-ray emission up to 30 kilo keV, we are even more in trouble because these are 30 arc second, of course. So all the possible contribution are within contain within the point-like emission. And when we go to GeV, our resolution is like 0.2 degrees. So you see that to discriminate the different contribution, which are all contained within few parsec, can be, I mean, it's basically very, very challenging. In general, what we are is lower angular resolution, lower statistic, and of course, it's also difficult to typically convince panels to get time, which means that, of course, when we are talking about sample studies, but that anyway we are we decide to undertake the challenge. When we talk about sample studies, we are talking about 20, 30 sources in total. So these are the number with which we are dealing, but still, after like, I mean, and of course, Chandra and XMM Newton were instrumental to really open this kind of studies. So after like more than 20 years of observation, we can say that in general, these sources indeed are detected in the X-rays and can be detected also with a relatively small amount of time. In particular, I'm showing here the result of the latest work on a CSO sample. There have been also other studies that were at the beginning focusing more on GPS and CSS, but we were seeing, in fact, that there was a high chance of contamination from blazars. So here is the last work led by Aneta Semijinowska on 16 CSO sources, which are relatively at moderate low redshift and young. And here in the plot, you see the X-ray luminosity and the age. And what you can see is that it's quite spread around, but in general, the luminosity are low or moderate, not super high super luminous source, very luminous sources. And the other general statement is that usually we do not observe a high level of variability, which is reassuring because in fact a high level of variability would point probably to strong beam emission and to a blazar contaminant. Then instead, moving to the continuum, the X-ray continuum properties, based on the sample results, what we see is that they are sort of boring sources because their spectra can be modeled with a simple power law modified for absorption, and the indices are typically very spread, and in part this is due also to the low statistic on which we are relying, that are compatible with both the accretion and the ejection scenario. Then in addition to the power law, for some of the sources, we also find that a thermal component is also required, sometimes multi-temperature, while the warmer thermal emission is usually most likely related to the host galaxy. For a couple of sources, we find also a hotter component, which is potentially interesting because, as I was mentioning, there is this idea that the interaction of the jet with the ISM can produce X-ray thermal emission. So the presence of a hotter thermal component is potentially indicating jet ISM interaction. Of course, since we cannot spatially resolve where the thermal emission is coming from, we need more information also from other wavelengths to really assess the interaction, the ongoing interaction. So then the majority of the sources do not show strong absorption, but there is a subgroup of sources which appears to be instead heavily absorbed. And this is interesting because in that case, we can use the X-ray emission to probe also the environment of the source. So staying on the sample results, what we try to do is to compare the results for unabsorbed and heavily absorbed sources. In this plot, what we are comparing is the size of the CSOs with their 5 gigahertz luminosity, and the color bar gives the absorption. So darker color are more absorbed sources. What we find is that unabsorbed sources with low absorption appear to be on a different track with respect to heavily or moderately absorbed sources. And in particular, the more absorbed sources are staying below the unabsorbed one. So there is there are two ways of explaining this result. On one side, we can say that these sources are embedded in a denser environment, which is somehow frustrating their expansion. So this is one point. And the other point is instead to say that for the same 5 gigahertz luminosity, the more absorbed sources, that for the same linear sizes, the more absorbed sources have higher 5 gigahertz luminosity than the unabsorbed one. And this could be explained if the most absorbed sources are, for example, highly accreting, and then they are characterized by, for example, powerful jets. So on one side, let's say the explanation is confinement from the medium. On the other side is a higher accretion rate, which is leading to more powerful radio structures. Of course, based on these results, we cannot really still differentiate between the two. So one other point is, of course, that, as I said, we are dealing with unresolved, spatially unresolved sources observation. And so how to be sure that the obscurer, the X-ray obscuring medium is located near the radio source, and whether it's located more close to the AGN or covering the full radio structure. So one test that was undertaken in this work was to compare the column density from the X-rays, that is tracing the total hydrogen column density, with the column density of the neutral hydrogen that is measured from the radio observation. Of course, radio observation have a better angular resolution, and we know that what we are tracing is absorption on the size, on the scale of the young radio source. So here they try to place, this is the H1 and this is the NH, the X-ray NH. And what they found is that there is a correlation, a positive correlation, meaning that in some way the two components are related, either cospatially or being part of a common medium. Then there is some spread, kind of a large spread, and this, however, could be due to some other kind of variables that are coming in when we estimate the H1. And for example, they are also putting forward some possible explanation to explain, to motivate this spread that is observed. Then in the last year, what I showed until now was mainly based on XMM and Chandra observation. So observation that are in the 0.3 to 7 kV band mainly. However, in the last year, we had the chance to expand the observation using NuSTAR that is observing also above 10 kV. Of course, the sensitivity is not the same, and only few sources can be targeted with the hope of getting a signal. But when we obtain a broadband spectrum, this is very useful, in particular, to discriminate between intrinsically flat X-ray spectrum or a heavily absorbed spectrum. And in general, we manage to constrain in a more precise way also the X-ray continuum. So this is an example of such a study where we see here the Chandra spectrum, and this is these are instead the data from the two instruments on board of NuSTAR. And we see that Chandra is heavily, there is absorption. There are also like a couple of, we added also thermal component, but in particular, this the addition of the inclusion of NuSTAR allowed to conclude that the continuum was softer than what was previously estimated based on only on the Chandra data. And of course, this is important also to understand the nature of the continuum. And on this source, I will come back a bit in the final part. This work in particular was done by Ettore Bronzini, who was a master student working with me, and now he studies a PhD. And some more work that is done by him, I will show later on also. So also, for example, in this source, the total modeling was showing the presence of a higher temperature thermal component. And this is a gamma ray detected source, so making more interesting the full picture of the interaction between the expanding source and the environment. Another source for which broadband X-ray spectrum was obtained is this one. It's another CSO. It's almost a Compton thick, so a heavily obscured source. And for this one, the broadband spectrum allowed not only to understand that the primary emission was reprocessed in different complex way from obscurer, but also to, let's say, we use the X-rays to probe the structure of the obscuring medium. That turns out to be a sort of medium with a toroidal distribution, possibly with clumpy clouds, organizing clumpy clouds. For example, here we have also the detection of a fluorescent KV emission line that is indicative of X-ray reflection. So in this case, on the cold medium that is surrounding the source. So to give you a sketch of what is the idea based on these X-ray studies, this is the classical case of an AGN, and this is the case of instead a buried CSO, where we see that even the lobes are still embedded in the dusty torus based on what are the current estimates of the extension of the dusty torus. And so if they produce X-ray emission, this X-ray emission would be then reflected by the dusty torus and produce part of the observed emission and be responsible also for the line that we observe. So this is, I mean, an interesting scenario that could be valid for the most obscured sources. Of course, we cannot rule out that the central AGN is also contributing to part of the X-ray emission. And this is despite the extension of the broadband, both cases are still, both scenarios are still valid. We could have a dominant AGN contribution, or instead the dominant X-ray contribution would be coming from the compact lobe. So just to summarize the X-rays, what we find is that in general, X-ray emission are returning a very heterogeneous range of properties. But where they are very useful are to probe the environment of the source and possibly the link between the source evolution and the density of the environment. What instead could help really to assess the nature of the high energy emission is the gamma ray component. Why? Because in this band, we do not expect an AGN contribution. A contribution from the AGN emission. We know that the corona emission is dropping well before the GeV band. And so when there is a detection in gamma rays, this is a clear smoking gun of the presence of a non-thermal component related to the radio structure. We have now Fermi LAT that is serving the gamma ray skies since 2008 and produce several catalogs. The dominant sources from in the catalogs are, of course, blazars. Why? Because in this case, the emission is strongly beamed, and the beam flux favors a detection in gamma rays. However, there are also handfuls, I think now is around 40 radio galaxies, so sources that are misaligned, which are not expected to have an aligned jet. Here we can play the game of finding the radio galaxies in the multitude of blazars, but I think we would become blind before counting all of them. But in general, this is already a proof that Fermi can also detect sources that are not strongly Doppler boosted. So with a lot of confidence, we went to look for detection of young radio sources in gamma rays. And in fact, actually, we were lucky enough because in 2016, we finally got the detection of this guy here. Is one of the most compact and relatively young CSOs. Here you can see the count map of Fermi. The cross is the position of the source. These are the error circle. And of course, you have always some contaminant that makes your life much more difficult, but we were confident enough in the end to confirm the detection. That was also then confirmed by the Fermi-LAT collaboration. After that, two other detections followed. And the sources are kind of similar, let's say. In this case, again, compact morphology, this is another source that is detected in gamma rays by Fermi. Again, compact and relatively young, but with a more jet-like morphology. And this is the third one. Again, compact, but in this case, there is a dominant radio core. So, plus there are a couple of others that are more debated, less confirmed. Then we try to move to sample studies. And of course, this is where I say that we had to consider also not only CSOs, because otherwise there are not enough not enough sources to have a meaningful study. So we extended also to GPS, CSS, and of course we included also quasars, not only radio galaxies. The study was based on 11 years of Fermi data, and we were going first for the individual detection, and then we stacked the signal of sources that were not detected. So in this map here, we have the sample. And the one that are marked in red are the detection. Sure.
Given that the sample is very heterogeneous, we have included CSOs, radio galaxies, aligned sources, misaligned sources. So what's the unifying feature of this sample? What makes it a sample?
Okay.
Just a collection of random sources.
No, I mean it's a collection. I mean there are several samples. And it's a collection of different samples. This is it. So there is a bona fide CSO young sample, but then there were other samples that were collected with different criteria. But it was.
So it's not a sample.
No.
Several
samples. Yes. For now, yes. And well, I mean, so. Let's go for the individual detection. Here is the plot where there is the gamma ray photon index and the gamma ray luminosity. We report 11 5 sigma detection. For the radio galaxies, 3 are the one that I already showed, plus there is one more, this one. And you can see that, so here is basically the red and gray are the blazar sources. Here is where typically stands the few radio galaxies that are detected by Fermi. And our sources, radio galaxies, are sitting typically among the radio galaxy sources. And they are characterized by low gamma ray luminosities and non-variable. Then conversely, instead, the quasar in the sample are sitting among the blazar locus, in the blazar locus, and they are typically also variable, meaning that probably there what we are catching is a blazar-like jet component. While for these sources here, the gamma ray detection is compatible with also what we expect if the emission is coming from an isotropic source, like would be the case of gamma ray emitting lobe. So when we consider instead, since it's a VLBI group, I was also showing the radio VLBI emission at 8 gigahertz against the gamma ray luminosity. So this is for the 3 CSO, the 3 bona fide young sources that have been detected, which are so display a lower radio luminosity than typical CSO, but one has also to consider that they are the most close by sources that we have also among the CSOs. So there is some bias in this finding. Instead, moving to the stacking analysis, we do not find a significant signal for the stacked sources, even trying a different kind of selection. Here, what I'm showing are the individual detection. These are the average upper limit for each non-detected sources, let's say. This is the gamma ray spectrum, and this is the upper limit that we derive from the stacking analysis. So as you see, we improve of about 1 order of magnitude with respect to the individual upper limit, and this allows to at least place some constraints on the models, and in particular. What we were able to exclude by comparing the prediction of the gamma ray predicted model for the lobe scenario, we were able to exclude the case of most powerful jets coupled with highly luminous highly luminous disk. So the idea is the following. We know that the gamma rays in the lobe scenario is produced by inverse Compton on the ultraviolet photons from the disk. We are able to estimate these luminosities, and comparing the estimates from the model with the upper limit, we know that strong, very high jet powers and very luminous disk, they should be detected. And since they are not, we exclude this part of the parameter space, let's say. Of course, one more meaningful comparison would have required better samples in terms of higher, more sources, and also more sources at lower redshift, given also the sensitivity of Fermi-Lat. In general, the indication is that young sources are gamma ray emitters, but they are weak gamma ray emitters, let's say. However, there was recently some surprise. I don't know how am I doing with the time, actually. Okay, no, I'm going into the end. There was some surprise because it was reported by the LASO collaboration, the detection of a low luminosity compact radio source at TV, and this was also presented recently in the conference. Here I'm just flashing these results because these sources are not specifically, we cannot say that they are young radio sources, but they are still low power and compact, and sort of unexpected as a TV emitters. Some work by Ettore also allow to conclude that the source is also detected in Fermi with a very low gamma ray luminosity. And the other source is instead a CSO candidate, which was also reported recently in by S as a TV detection, and that on which we have an ongoing multi-wavelength follow-up. So the excitement is that we really do not expect TV emission from this kind of sources, and so it's something really new and possibly interesting for the future. So to summarize, the gamma ray, as I said, the CSOs are gamma ray emitter, and so this means that there is a non-thermal high energy component. although probably they are not exactly the strongest gamma ray sources. So just to conclude, I would like to show how the detection, the study in X-rays and gamma rays then can be put together with the multi-wavelength datasets to have a proper modeling of the sources. And these are both two gamma ray detected sources. One was the first that was detected that has a mini lobe radio structure, and for which we tested the lobe scenario model, which was able to successfully reproduce the gamma rays, but where we see that the X-rays is a mixture of non-thermal inverse Compton on the dust, on the infrared photons from the torus, and a weak X-ray corona. Similarly, in this case, for 3894, the model that was applied by Ettore was instead a jet model, because the morphology is jet-like. And in this case, the X-rays, the gamma rays are due to synchrotron self-Compton, while what we see is that it was very hard to reproduce the X-ray emission if associated to the jet, and then but instead we could model them assuming again the presence of a weak corona. So in this case, gamma ray and X-rays are dominated by two different components. In one case, the jet; in the other, the AGN. But in general, for both sources, the jet powers that we infer are relatively low, meaning that it's not granted that this source will be able to expand beyond the host galaxy. And just to say also, even upper limit can be useful in this modeling, even providing loose constraint. And this was another work led by Dominika Kroll at CFA on the role of the torus in producing the X-ray emission. So I come to the conclusion. What I want to, the message that I want to deliver is that X-rays are indeed useful to understand better how the radio sources are evolving and how they interact with the small-scale environment. Now, the next step, I mean, the ongoing work is to try also to have detection in X-rays for higher redshift sources, and at the same time also to go lower in power. Then, in terms of future steps, of course, beyond the comparison with simulation, what we really need, as you may understand, is larger samples. I'm not very worried for the radio. I'm confident for the gamma rays. Actually, for the future of the X-rays, I put a question mark, because we don't know exactly what kind of instrument will give us, I mean, in the future, will help us in this kind of studies. To conclude, just a modest proposal. There is a series of GPS, CSS, Young Sources workshop that is ongoing, and there was one some years ago in Greece. It was some years ago because in the web page were saying the currency is now euro, the old drachmas have gone. So maybe it's the time to renew the tradition with a new workshop, and I leave it for the organizer of the conferences here.
Any questions? I have a question about the reflection model that you mentioned. Whether you have the X-rays produced from the accretion disk itself, or from the lobe. Would you expect different variability patterns in the two cases?
So when she said that you were probably here, I had this slide. I'm just kidding. But it's true. So, because I know my my chicken everything. No, yes, this was a sketch that was done by my Gosha. But we see some variability in this source, and it's true that can be explained in terms of variability due to the obscurer. So probably in terms of it will be very difficult to discriminate based on the variability, because on one side we expect a slow change of the X-ray continuum with the expansion of the lobes. But at the same time, if the medium is inhomogeneous, you can have also variability on shorter time scales, probably due to the change in the line of sight or the moving of the clumpy medium. What was also another thing that it was considered is that possibly, but it's too weak for XP, for example, polarization could be different in the two cases. But unfortunately, we have an X-ray polarimeter now. We need a more sensitive one. No, I see. Jan is saying no.
Check.
Yeah, no, I was sure.
One last question.
Time to eat. We can.
But they're both very quick ones.
Yeah.
So the first one is for the sources of TeV emission was detected. Is there also GeV emission?
So this, let's see. So for this one, at the beginning it was not. Then Ettore went really to look through the data, looking at the right time, and he found, but it was like I think 2 photons in the very hard. It's super hard, and is compatible with what you expect, like a very quickly rising hard component. Yes, but also very hard. And this one is in the Fermi catalog, and it's variable. So.
And then the question is, when you show the stacking, what did you stack? Did you say again?
So we stacked only the sources that were below the threshold, the detection threshold.
What kind?
These were all, I mean, we took the whole sample, but we were trying different combination. For example, only CSOs, only sources up to this redshift. So this was for the radio galaxies. Okay. Yes, only for the radio galaxies. Yes.
And then do these have very different redshifts, or are they all
so the radio galaxies are I don't remember the full range of redshift. They are for sure the one at the lower redshift, but it's yes.
I have one that is, so you name in this study young. Do you have information?
So for some, yes, there were the kinematic, yes, but for the tiny, I mean, not for the, no, yes, because the total what was 100, 160, and we know that we don't have, the other were based on the spectral, radio spectrum in particular. So GPS, CSS.
The spectral, you refer the spectral age or the...
Both, yes. No, yes.
Okay, I think we can move here. Let's thanks.
Thank you.